Hi everyone, Steven here. Welcome to another MATLAB Crash Course series lecture. Today we're going to look at writing scripts in MATLAB. So I'm going to cover a few topics here with this lecture. First we're going to start off with the purpose of scripts, why we write them, what they're used for. Then we're going to look at how to actually write scripts and how to write simple programs through scripts. Then we're going to take a look at documenting scripts, and then we're going to finally end it off with some user input and output with scripts, and along with a few examples. This lecture is very example heavy because it's the best way to actually learn what scripts are used for, purely through examples. And then we're going to finish it off by talking about an introduction to functions and what functions are used for in MATLAB. So first I'm going to talk about the purpose of scripts. So the command line is very useful for quick calculations, but tends to not be as useful when more rigorous actions are needed. So essentially everything we've been doing up at this point with all these lectures and different videos, everything's been happening. Oops, sorry about that. We got a few things going on here. They've all been happening through the command window. Everything we've been doing so far is through the command window. Purely this right here. Every time we want to do a simple calculation or create a matrix or do user input or fprintf or any of that stuff, we've done it purely through the command window. And the command window can be useful, but it's not very effective when you want bigger calculations or calculations that take multiple steps. The command window just isn't going to cut it. That's when a script comes in. So a script, and for MATLAB it's known as a .m file, kind of like a .txt or .docx for people that use Word. It's a .m file. But so scripts consist of multiple lines of code that are acting as steps to provide a solution to some type of problem. So essentially, instead of breaking it up in the command window, so in the command window previously, we've been doing like assignments like var equals 5, then we type another assignment, mat equals 4, 5, and things like that. Every time we type a line of code, we click enter and something happens, or we assign a variable and all that. But what the beauty of a script is you can type lines of code without having to immediately get a result. Instead, you can type a line of code, have it just exist, and instead type multiple lines of code, however many you want, hundreds even, and have them all run at once without having to click enter every single time you want to do something or run a line of code. What's even better is you can save these lines of code and you can use them multiple times without having to type them out each time. That's really the beauty of a script, and we're going to look at how to write one real soon. But so a key note here is that many scripts will utilize algorithms, or a series of steps which are generally mathematical, needed to produce a solution. Many scripts do not just exist, and many people when they write a script won't just be like, okay, I want something to happen, it'll happen automatically. Generally, you need to lay out a formulaic plan to know exactly what your problem is and how you want to solve this problem. If you don't identify the problem, identify the steps needed to solve the problem, writing a script is going to be a lot harder, and it might be even more tricky in the end, even trying to write a script, than just maybe doing it by hand. But developing a key algorithm or the steps needed allow us to identify how exactly we need to produce code to get something to work. A user will run a script, meaning that the code will be executed in a step-by-step pattern. It can be thought of multiple lines being entered in the command window at once, and we already discussed that a bit. So how do we write a program through a script? Well, a simple program can be written through a script in MATLAB. The general format consists of beginning with some type of starting value, and through various steps, working your way towards a final value. With MATLAB is a very mathematical programming language. It's used to help with research, it's used for plotting, a variety of different things. But what makes MATLAB so easy is that it can easily compute mathematical operations. And it's very user-friendly, in which that one can learn how to use these operations very easily. Generally, someone's going to have a starting value or have something they want to try to find or a problem they want to try to solve, and through multiple steps, someone can use MATLAB to actually get towards their final value. We're going to do examples towards all this to see how exactly this can all be used. All programs have a purpose to fulfill. Whoever creates the program must develop an efficient and effective method such that this purpose is fulfilled, which is generally the heart of programming in general. You have a problem you want to solve, and in an effective and efficient way, try to make it so you can solve this problem, and make it so that other people can solve this problem more easily because of your code. And here's a quick example we're going to use to get this started. Create a script to find the volume of a sphere with a radius 6. This could easily be done in the command window, but this is just a very quick example to show how a script can be made. So we're going to take a look at MATLAB here. I'm going to clear the variables I have. I'm going to clear the command window. So to start a script, what we're going to do first is make sure you're in currently the folder you want to be on your computer. At the very first episode of MATLAB, I talked about the folders you want to be. But just to recap, if you click this folder with the green arrow, you click this here, it will take you to your current directory, all the folders that exist in your computer. Like I said in the first lecture, you want to make sure that you save all your work in a folder that will help you. I'm going to do all my work in currently the folder I'm in right now. It's in my documents and in my MATLAB folder. I have other folders in this folder, but I'm going to keep the code right now in this folder. Make sure that you store your code in a place where you're able to locate it. Create a new folder entirely for your code, and for these examples, it will be much easier in the long run. It'll help identify what code is used for what later when you start writing multiple scripts. But so for right now, I'm going to keep it in the folder I have right here, so I'm not going to worry about this. So the first thing you're going to want to do is click this button up in the top left corner, or you can press Control N, and this will create a new script. So you'll see my screen's essentially the same, just a few changes. So my command window kind of shrunk. It used to be this whole thing, but it moved down here. And what filled up the rest of it, or the remaining, is this, what's known as the editor. The editor, like it sounds, is a place where you can edit scripts or .m files. Currently, the file I have saved is titled untitled, meaning it's not titled anything. I don't know why I said titled. But so what we're going to want to do, the first thing we want to do is give this a title. Your code actually will not run if you don't give your code a title. So we're going to first immediately start by saving this script. And so I'm in the folder I want to be, which is good. But it will ask you which folder you'd like to save your code. Like I said again, make sure you know where you would like to store your code. We're going to be calculating a sphere volume. So I'm going to call this sphere volume. I don't need to worry about typing the .m because for me personally it saves as type .m. If you use a different computer, you might need to specify. I'm going to save. So now the name of the script is spherevolume.n. The path, meaning the folders that are used to take you here, can be shown right here. It's all the folders that exist in order to get to this script. But so here we start, and so the prompt asked us to calculate the volume of a sphere with a radius of 6. It doesn't really matter what units we're using because we're going to assume it's just unitless, possibly in the XY coordinate plane. But so how would one maybe calculate this problem? What's the algorithm we're going to use? I'm going to develop more series algorithms in later slides. But so let's see what we can do here. So first, let's actually establish what our radius is, because we have a radius of 6. In MATLAB, you can store numbers as variables. So what we can do is we can start by naming a variable radius, and we can say radius equals 6. This can be our first key. This step isn't necessarily necessary, but is it necessarily necessary? It's not necessary, but we're going to use it just to establish what good common coding practice is. Then in the next line, now that I have my radius, I can actually calculate the volume. And what I can do is I can simply assign a new variable as volume. And I can say that volume equals, and then we have to calculate the volume using the formula for a sphere. For people that don't remember, the formula for a sphere to calculate its volume is 4/3 times pi times the radius cubed. So we can type exactly this. We can say 4/3, which I'm just going to put in parentheses 4 divided by 3, times pi, which in MATLAB is denoted by simply the word pi, which is 3.1415. MATLAB has all the digits saved, or as many as necessary. 4/3 times pi times the radius cubed. So we can put radius in parentheses, and then we can cube it using the caret for the exponent, as well as the number 3 for cubing it. And this is actually all we need to do. Now we need to run this script. There's a few ways you can run this script. The easy one that may appear right off the bat is this little green play button here, which says run. What this will do is this will run your script, meaning it will start at the top line of your code and work its way down to the bottom. One more thing before we run it though. If you look at the name sphere volume here, you'll see there's a little asterisk by the M for .m. That asterisk means that currently your work is not saved. So if you'd like to save your work, you can click that save button. Watch what happens to the asterisk here. When I click save, that asterisk goes away, meaning that your work is fine. MATLAB is very good about making sure your work is updated and will be saved. If I had just run the code, it would have automatically saved anyway, but it's good practice to keep saving in case something happens or your computer blows up or anything like that. But so this is the code we have. if I click run, so some stuff kind of happened here in the command line, the command window. Let's actually see if I can exit out of my editor just by clicking this X. It'll save my script because it's currently saved over here in my folder. So let's see what happens. So I have a radius of 6. My volume, it says, is 9.047786842, a bunch of digits, times 10 to the second, which, as you can see over here, because my variables are saved, is 904.777, which more or less checks out. So that's the volume and that's the radius of my sphere. Did exactly what I wanted. But so this format isn't exactly the nicest, though. What we're doing right here isn't generally the most practiced of coding. Generally, it's nicer to have your output formulated in some way or displayed to the user in some way to make it all look pretty. We're going to talk about that in a few slides. One other thing I'd like to notice, though, I'm going to go back to the editor by just double-clicking my script here. You probably notice these highlighted equal signs here. If I hover over this, it says there's a warning. It says terminate statement with semicolon to suppress output within a script. So what does that mean? So if you can see here, I assigned 2 variables, and down here in my command window, both of those variables were displayed. Radius equals 6, volume equals this. My variables were just simply displayed. I might not want all these variables to be displayed. I might only want the volume variable to be displayed, or I might want none of the variables to be displayed. So in order to prevent this, what I'm going to do is I'm going to place semicolons at the end of these. If I place one here and I place one here, you'll see those equal signs go away. Your code will still work if you don't put semicolons, but watch what happens now if I do put semicolons. And then this is actually another way you can run the code. I'm going to use that for example. So if I actually just type the name of the script, if I say sphere volume, it will automatically run my script. And then nothing happened. And the reason nothing happened is because we put semicolons at the end. The semicolon essentially means that variable assignment, don't display that assignment to the user. So these 2 assignments here, because we put those semicolons, they were not displayed to us. However, they're still saved in the workspace. I think they were already saved to begin with, so I'm going to do this example one more time. Let's say I clear my workspace, and I say sphere volume. These 2 variables then pop up. The radius and the volume were calculated, and then they are saved. But so, like I said, this isn't the best coding practice. What is good coding practice is placing semicolons. Placing semicolons is, you always want to do that. Whenever you're writing script, whenever you create a variable in a script, always place semicolons at the end. The user does not want to see every single assignment you make, every single variable assignment. It's not necessary, so please place semicolons at the end. But for the rest of us, it's not the best coding practice. We just put a variable and then we just calculate the volume. That's not necessarily the best or most efficient thing. We could have just done this in the command window. What is more impressive, though, is say we ask the user for a radius, and then the user enters a radius, we calculate the volume ourselves, and then we print out the volume in a nice sentence. That's something that's a little more tricky to complete, and something that can't just simply be completed by using the command window. So let's actually see how we could accomplish something like this. Oh, but first, one other thing I forgot is how to document our scripts. So scripts are much more useful if the creator provides substantial documentation to supplement the code. Essentially, the documentation are comments in your code. Basically, what you do is if you write a code or write scripts that someone might want to use later, what is good practice is to leave comments in there. Comments on what the lines do, what the script does in general. To type a long comment, or to leave a comment in MATLAB, type a % at the start of a line and then proceed to type your comment. It's as simple as that. If I go to this script here, I'm going to leave a couple spaces. I can actually type a comment. If I put a %, my text turns green. And I can say, let's say generally the first comment you want to place in your code is going to be a comment that tells the user what the code does. So I can say this script calculates the volume of a sphere. And then let's say down here, I can place another comment that says assign the value of the radius. And then I can say here, calculate the volume using the sphere volume formula. So this is something that could tell the user exactly what my code does and what each part of my code does. As you can see here, if I save my code, this code can actually be used to tell the user what my code does from the command window. I'll show you what that means. So let's say This is what my code looks like now. Look at this first line. This script calculates the volume of a sphere. Very straightforward. If I type help and then the name of my script, sphere volume, it will actually print out the first line or first few lines you have as comments in your code. So it says this script calculates the volume of a sphere. It prints that one. It didn't print any of the other lines of code because of this space. But any lines of comments before a space are going to be printed in the command window. And documentation and leaving comments is very useful when you're writing code. And we'll have more examples with this. All documentation at the top of the code will be displayed using the help function. To type a long comment, begin a line with a %, then a bracket, and end the comment with a % and a closing bracket. So we can actually try this. Let's just try this down here as a test. I can say %, opening bracket. I could say this is a long comment. And then I can finish with another % and a closing bracket. And so it kind of bottles it all up. I can even enter and say, here is another line. I don't need to leave multiple %. It knows this is all one big chunk of code. I'm going to delete this because it's not really pertinent to our example. I'm going to save. And so that's all about documenting code. Make sure when you're creating projects or labs, you do document your code for your own sake and for the sake of anyone that might be grading you or using your code for anything in the future. Now we're going to look at the example I had earlier with how can we ask the user what we want. The various functions used for user input and output can be utilized to create a script that can interact with the user. Many basic programming scripts may begin by asking the user to enter some type of value. If you remember my last lecture, lecture 6, we talked about user input and output using the input function, using the display function, and using fprintf. If you do not remember those, I suggest you go and check out my last lecture, lecture 6, user input and output. These different functions can be used to help us ask the user what they want, not just a value we want to assign. The script will then save this value to potentially perform calculations. Certain information may then be printed to the command window by using fprintf or display. These tactics are useful for beginning programming, but generally these tactics are not recommended for advanced code. We're going to be using input, we're going to be using fprintf, but as you use more advanced code, these types of methods of getting values from the user are not recommended. There are better ways to do it, and those ways are through functions, which is something we'll discuss a little bit in this lecture and more on lectures to come. But so I'm just going to start off, I'm going to continue this by doing 3 main examples that are going to increase in difficulty as we go on for writing scripts and how we'd go about the process of writing these scripts. So the first example, create a script asking the user for a value in inches. Have the corresponding value in centimeters be printed to the command window. So let's see, so we want a script that will ask the user, hey, enter a value in here in inches. Then we're going to print another line saying the corresponding number of centimeters is, and then print whatever value they entered, we must convert that value to centimeters. So let's see exactly how we go about doing this. And this is where we start to develop an algorithm. So the example 1 algorithm. While the problem seems straightforward to calculate by hand, we must understand an algorithm to accomplish it by using MATLAB. So let's see, the first step here is to write code to ask the user for the value associated with inches. That's the first thing we want to do. The first thing we could possibly do, we don't have any number to work with, we must get a number from the user. And that's the first step we're going to have here. So let's look at MATLAB. I'm going to exit this here. We're going to create a new script. And this script is going to be converting inches to centimeters. So I'm going to save it, inches to cent. We'll just say cent for centimeters. Excuse me. So in this case, we have our code here. The first thing we can do to help us understand more is leave a comment saying exactly what the script does. So we can say this script will ask the user for a value in inches and convert to find the corresponding number value for centimeters. Doesn't need to be too in-depth, just something so that any other person would know exactly what the script is doing without even having to look at the code. Put a period just for fun. This is where we start looking at how do we accomplish this. So the first thing we need to do, like I said, is ask the user what value they want. So let's leave a comment saying Ask the user for the value in inches. That's going to be the first step here. So what line of code would accomplish this? So to ask the user for the value in inches, let's assign a variable. We can say this variable is inches. The value here, the value going to be stored here is the value that the user enters when using an input. The input is accomplished by using, I think I put it in the side, by using the input function. We use the input function, like we learned in last lecture, to actually get a value from the user and use that value. So we could say inches equals, and then we want the user to enter a value. So we could say input, enter a value in inches. And then we can leave like a space for them and a colon, and then the user will enter a value in inches. And we're going to put a semicolon because once we get that value in inches, we don't want a statement saying inches equals 2.01 or whatever the user entered. So we get a value in inches by this line here. Inches equals input, enter value in inches. So whatever the user enters, it will be saved as the variable inches. The next step here is use the value to calculate the corresponding number of centimeters. So once we have our value in inches, there's nothing stopping us from just finding the correct number of centimeters. Multiply the previous value by 2.54 to convert. Since there's 2.54 centimeters in 1 inch, every inch we need 2.5 centimeters, so we have to multiply by 2.54. This can be accomplished by, and we can leave a comment here, convert from inches to centimeters. Let's save another variable for ourselves, centimeters. This variable will save the correct number of centimeters that corresponds with the number of inches. Centimeters equals, so how do we get to centimeters? Well, we need to multiply our inches by 2.54. So we take whatever value we got from inches, which is what the user entered, multiply by 2.54. That's going to give us the number of centimeters. And we put a semicolon so we don't have a line saying centimeters equals some number. So we have that. Let's see what the final step we have to do is. The final thing we need to do in this problem is print to the command window. We need to print saying the corresponding number of centimeters. We can do this by saying use fprintf to print the value as a type float with 2 decimal places. We'll use 2 decimal places because 2.54, significant figures, rounding, and all that. So how do we do that? We'll say print value to command window, and we can do this by using fprintf, and we can say value in inches. We'll put a colon, and then we want to put our value here. If you remember from the last lecture, when using fprintf, we want to put a placeholder and put it to 2 decimal points, 0.2f. We'll put the dash n so that we started a new line, and then what value are we going to want to put in the space? We want to put the number of centimeters, which is found in this variable here. So we'll type centimeters. Centimeters. I think that all looks right. Yes. So this is exactly what we have to do. So let's take a look and see, and make sure I didn't mess anything up in here. So I'm going to save this, and then I'm going to exit out of my command window, and I'm going to run the script, say inches to cent. Enter a value in inches. Let's see, what's a simple value I can do? Let's do 2. So I'm going to say I have 2 inches. Value in inches, 5.08. And 2 times 2.54, that seems like it checks out. And our variables are still stored here. That's because this is a script, so all your variables will still be stored here, which is okay for now. You can simply clear the variables later. But so this program does exactly what we expected. We can try it again and try maybe something a little more complicated, something that isn't something we can do in our head. Inches to centimeters. Let's say we have 546.2315 inches. If I click enter, it gives me a corresponding number of centimeters rounded to the nearest 2 decimals. It works exactly the way we expect it. It works pretty darn well, I'd say. This is exactly what writing a script does. We can do multiple steps at once. Ask the user for an input value, display that value to the user. It all works very methodically. It works very well. I'm going to clear all the variables we have, clear the command window. That was our first example, and it was a fairly straightforward example. Now we're going to get into a little more complicated example. Imagine a scenario in which someone is throwing a ball upward at a specific launch angle relative to the horizontal. So we're imagining someone's throwing a ball relative to the horizontal. There's an angle we're throwing it at. We're throwing it at a specific launch velocity. Using user input values for both the launch velocity in meters per second and the angle given in radians, calculate the maximum change in height that will be achieved at launch. And I think I actually want to make this a little bit different. I want to make it so that actually, because radians are a little tricky to know, we're going to make it so that the user enters it in degrees. Calculate the maximum change in height that will be achieved at launch. Assume negligible air resistance and downward gravitational acceleration of 9.81 meters per second squared. So this one seems like a bit of a physics problem, but it definitely seems like something we could do in MATLAB. But instead of just asking for one value from the user, we need to ask for two separate values. We need to ask for the launch velocity, the absolute velocity at some direction, and the angle in which it's being thrown in degrees. So let's see what we have here. So we are going to develop an algorithm. I have some standard algebraic physics 1 equations used for kinematics that one might be familiar with. We're going to use a couple of these. So first, ask the user to enter the values for the launch velocity and launch angle. Velocity being v, angle being theta. You can see in this fourth equation here that vy equals v sine of theta. So remember, we need to develop an algorithm and know exactly what we're doing. If someone throws a ball upwards and throws it upwards at a certain angle, at a certain speed, we can use these equations to know exactly when the ball is going to go upward and then stop going upward. And the way we calculate that is by looking at its vertical distance. Once again, if you have not taken high school physics, they might be a little confusing at some point if you have not taken algebraic physics. But essentially, when you throw the ball upward, the gravity is going to decelerate until its upward velocity, because a ball, when you throw, is going to have an upward velocity and a horizontal velocity. The horizontal velocity is constant. The upward velocity changes due to gravitation going down. So we have here is we're going to throw the ball upward, and at some point, that ball is going to go up and up and up until it stops, meaning its upward velocity is 0. We want to find that time when the upward velocity is 0. So use equation 4 to calculate the initial upwards velocity. So the initial upwards velocity is the upward velocity right when you throw it. So not the absolute velocity, but what fraction of that velocity is pointed in the upward direction. Use equation 1 to calculate the amount of time necessary for the ball to reach the max height, since the upward velocity at that time will be 0 meters per second. So at the max height, we know the upward velocity is going to be 0 because it stopped in midair. To find that time, we're going to use this first equation. We know what the initial upward velocity is. We know what the acceleration in the y direction or the up and down direction is. We can find the time it takes to reach that highest point. Then we can use equation 3 to calculate the change in height at the previously calculated time. So equation 3 tells us that the change in y, or vertical distance, is equal to the initial throw velocity times the time, plus 1/2 the acceleration, which in this place at this point is 9.81 meters per second squared downwards, times our time squared. If we do that, we're going to find exactly what our change in height is. And this change in height is going to be the max distance. That change in height is going to be what we calculate for. Seems like a complicated process, especially if you have not taken a physics course. I'm trying to do best I can to try to explain these concepts. If you have not taken Physics 1, algebraic physics, kinematics, if you have taken it, hopefully some of this is clicking a little bit back and these equations look familiar. But so let's start at the beginning. The first step, we need to calculate the vertical initial upward velocity using this equation here. Well, technically, first we need to ask the user for the launch velocity and the launch angle. So let's create a new script, and let's see, what should we call this script? If we save it, let's just call the script physics, just physics for now. So we have our script physics. We could say this script will calculate the maximum change in height given an initial launch velocity and launch angle in degrees. Okay, cool. So the first thing we're going to want to do is ask user for requested variables, which is going to be the launch velocity and the launch angle. So we're going to use that input function again. So let's see, what do we have here? We have a launch velocity and we have an angle. So I'm going to consider the launch velocity as just v. That was the same variable we used on the slide here, v right here. That's going to be what I store it as. So we're going to say v equals, and we want to ask the user. Asking the user means we're going to use that input function. Input, enter initial launch velocity, meters per second. Just gonna specify so the user knows it's in meters per second. Just like that. That's gonna give me my value for V. We also want a value for the launch angle. I'm gonna call that just, let's just call it angle. So we could say angle equals input, enter initial launch angle in degrees. Let's put a colon there, and just like that. So now the user understands. So then one thing we want to make sure we understand here is that we are going to be using the sine function for this angle, but MATLAB can only take angles in radians, and we ask the user for degrees. So the first thing we should do is convert the degrees to radians. So that might be the next step we have here, convert degrees to radians. And so all I'm going to do is I'm not going to make a new variable for this. I'm going to actually reassign the old variable we have. And hopefully this won't be too complicated. This might be the first time I've talked about this in this lecture series. But I'm going to say angle equals angle times, and then to convert from degrees to radians, we multiply by pi over 180. So I'm going to say pi divided by 180. So this might look a little weird because I put angle twice, but let's look at it. What we do is we're saying, okay, plug in the value we currently have for angle. Multiply by pi over 180. That's going to give us a new value for angle. So I am redefining what the value is just so I don't have two angle values. I had an initial angle value in degrees. I changed it, so now it's the angle value in radians, but it's still the same name. It's one less variable we have to worry about in the end. So now we've converted it from degrees to radians. The next thing we're going to want to do here is use equation 4 to calculate the initial upwards velocity. That's used by this equation. So we need to use both those variables we just got. So I'm going to call the upward velocity. So let's see, we can say calculate, oops, let's put a space there. I'm going to put calculate upwards velocity. So upward velocity, I'm going to call it Vy, is going to be equal to V times, because V was our velocity, times the sine of our angle being the new angle in radians. So we have exactly that. Now we have the value for Vy. So we got number 2 checked off. The next step, use equation 1 to calculate the amount of time necessary for the ball to reach the max height. So let's see, what do we know? We know that at the max height, the value of Vy is going to be 0 because the upward velocity will stop at the maximum height. Our initial upward velocity is the velocity we calculated for, Vy. Excuse me. We know that AY is going to be 9.81, but not positive 9.81, negative. Since we're looking at upwards, up and down, we know that the acceleration goes downwards in the down direction, meaning it has to be a negative value. There we can calculate for t. So let's see here. If we look at this carefully, we want to find t, but this equation gives us it in terms of Vy. That means we want our new Vy, which is going to be 0. We're going to subtract over this variable here, the Vy naught. So we're going to subtract over, giving us Vy minus Vy0. Let's see, maybe I can try to write this out. It might not look too nice, but let's see. So we know that Vy, if I subtract, I get Vy0. If I subtract that over. And then to get what t equals, I got t, oh geez. Erase that. So t, oh my word. T is going to equal these two subtracted divided by, oh my word. This drawing with the pad isn't exactly working. Divided by AY. That's supposed to be AY. I apologize. All right. So essentially, this is the equation we want to use. T equals Vy minus Vy naught divided by AY. All right, so let's actually type exactly that. So next we're going to, and I'm going to leave a comment so you know what we're doing, calculate time needed to reach maximum height. Let's call that time t, just so we are consistent with our variables. So t is going to equal, so let's look at our equation here. Vy here is the final upward velocity looking at our time frame. Our final upward velocity, once the ball reaches its maximum height, is 0. So we don't really need the 0 here, but I'm going to use it just to display this. So it's going to be 0 minus our initial launch velocity, which is currently Vy, divided by our acceleration, Ay. That's going to be negative 9.81, which is why we get exactly that. It looks a little wonky with the divided by and the minus. So we're going to say divided by negative 9.81 in parentheses. And that's how we get our time. The last step we have is calculating. I'm going to erase this because writing that's going to give me nightmares. We got all of that. Exit. It's going to ask me to save my changes. I'm going to say no. It's going to like reload again because that's what this does. I use Microsoft Edge. I don't know why. But so essentially the last step we have is to use equation 3 to calculate the change in height at the previously calculated time. And the previously calculated time was in fact that time we just calculated, whatever t equals. And we use this equation. We say delta y equals Vy naught, the initial upward launch velocity, times our time, plus 1/2 times the Ay, which is negative 9.81, times our time squared. And that time we just calculated in the last step. So let's go back to MATLAB and do this. So the last step, calculate change in height. I'm going to call the change in height y. So we're going to say y equals, using our equation, we know it's the initial launch velocity, which is Vy, times what our time is. So I'm going to say in parentheses Vy times t. That was the time we calculated. Plus 1/2, instead of 1/2, I'm just going to say 0.5. Times our acceleration, which in this case is negative 9.81, times our time squared, which is time to the second power. And this is exactly the steps I need to do. So y is my final answer. Y is the upward change in height that we achieve, the maximum change in height. Now there's one more step we have to do. The final step, print the result to the user. So that means that we're going to just simply type that print result to user. So in order to print the result to the user, we're going to use fprintf again. So using fprintf, we can say fprintf maximum change in height in meters, and then we're going to print it. We can say print, it's going to be a float value again. So we're going to say the 2 decimal places again. Put the -m. In fact, we can do one better. We can actually put the word meters after, so it looks nice. So meters, put -n to say we're going to start a new line. Then we need to specify what our value is. So let's see what value we're going to put in. Oh, and I just put 0.2. This should be 0.2f because we're dealing with a float type here. And the value we're going to put here is going to be y, which is our change in height. And now we have our final script. The only way to see if it works is to, well, check it and see if it works. So we're going to save it. I'm going to exit out of here. I'm going to start my physics script by typing physics. Enter initial launch velocity in meters per second. I'm going to say my initial launch velocity is 100. Enter an initial launch angle in degrees. I'm going to say we're throwing it at a 55-degree angle. The maximum change in height in meters is going to be 342 meters. And that seems like it would be something that makes sense. It seems like it's all good and our math checks out. So once again, our algorithm is efficient, and we were able to do so in a way where we could clearly list out our steps and show every step that was needed to solve this problem. It wasn't just a simple one equation solves all deal. It was we had to ask the user for values. We had to calculate a new angle in radians. We had to use a couple equations. We had to use a third equation even. And then we had to print the value. These were multiple steps. We couldn't have done all this in one line in the command window. Or we'd have to use multiple semicolons and make sure it's all okay. We would only get one try at it. In this case, we can type this and we can run it as many times as we want to. We can just type physics again. We can run it another time. I could say 3 and I could say the angle is a 23-degree angle. And it all works exactly the way we'd expect it to. So I have one more example, and this one's probably the most complicated example, but hopefully one that's really interesting and allows you to think a little bit more. So I'm a chemical engineer, so this example is a little more chemical engineer related. Let's give it a go. You're working at a chemical plant, and you must keep track of streams of benzene, toluene, and cyclohexane. The user can pick one of these three substances to choose from, and then the user can enter three linear velocities in meters per second. Then the user must enter three separate cross-sectional diameters for the pipe in centimeters. With this information, calculate the three mass flow rates of the three separate streams in kilograms per second. The densities of benzene, toluene, and cyclohexane are 0.876, 0.867, and 0.779 grams per centimeters cubed, respectively. So this is quite a bit of information to get thrown at right away, but let's take it down one at a time. So there are three different types of streams we can look at. We can look at benzene, toluene, or cyclohexane. The user can pick one of three of these streams to analyze. So for example, let's say we're looking at just benzene. The user then must enter three linear velocities for three separate pipes. All three of these pipes, though, are going to be strictly for benzene because we picked benzene at the beginning. So the user picks benzene, and then they type, okay, hey, we have three separate pipes that contain benzene flowing through them. They each have a linear velocity of some value in meters per second, like 5 meters per second or 0.6 meters per second. With this information, the user then must enter three separate cross-sectional diameters for the pipe. So essentially, we have three of these pipes, and each of them have a separate cross-sectional diameter. So if you think of a pipe going through, the pipe has a circle for its cross-section. Each circle has a diameter. So you have three separate of these diameters. With this information, calculate the three mass flow rates. So each mass flow rate for these three pipes in kilograms per second, given these separate densities. Now, for people that have taken chemistry, Chem 109, or any chemistry class that you could possibly think of, this might be a little familiar with densities and looking at volumes and all that and calculating the grams. We're going to take a look at it. So let's look at our algorithm first. First, we ask the user which of the following substances they'd like. We can use input for that. And in order to do that, we can assign each substance as a number 1 through 3. This is going to be the most effective way to do it, as you'll see. If we assign each substance as 1, 2, and 3, we can say benzene is 1, toluene is 2, cyclohexane is 3. We can ask the user to enter the number corresponding to it. This will be a lot easier for purposes of all we know right now. Down the road, we might have more effective ways of doing it, but this is going to be the most effective right now. We can then save these densities as a vector in the script. So there were the 3 densities we looked at. We can save these as a vector. So then the correct one can be accessed by using the correct index given. So essentially, we can create a 3-length vector. We can make a vector with 3 separate values. We can make those values these 3 numbers here. The first value will correspond with benzene, the second with toluene, the third with cyclohexane. The reason we assign these substances as 1, 2, and 3 at the beginning, like I specify up here, is so that if the user puts 1, we can access the density of benzene by saying density and then in parentheses 1 using indexing techniques. Let's actually start simply by doing that first. That's going to be the first part of our step. So let's create a new script. We're going to save it. I'm going to call it mass rates. This script will calculate 3 separate mass flow rates for 3 separate streams of either benzene, toluene, or cyclohexane. So first, ask user for, actually the first thing we're going to do is save all the densities we have. Save densities as a row vector. So let's look at the densities that we can look at here. So we had the 3 listed. So I'm going to call these densities, I'm going to save it as a vector called densities. And it's going to equal 3 separate values in my vector. So let's see what the densities were. 0.876, 0.867, and 0.779 for benzene, toluene, and cyclohexane respectively. So let's save those values. So we have 0.876, I think 876 was first. Yep, 876, 0.867, 0.779. So those are going to be the 3 separate densities, and you're going to see how all this kind of comes together in a second. So we have all those saved. Then we're going to ask the user to select a substance. Let's see how we do this. So first we're going to display exactly what this is. So we can say fprintf choose a substance to pick from. I'll just put a period. I'm going to put -n so we go onto the new line. I'm just putting this just so that we can actually show our options to the users. I'm put a new line that says fprintf 1 colon benzene. I'm just listing out our options here. fprintf 2 colon toluene -n. fprintf 3 cyclohexane. So we listed out all of our options we have here. Then we're going to actually get one of these values from the user. I'm going to call it substance. Actually, no. Since it's a number here, we're going to make it just a small, I'm going to call it n. So n equals input select substance using the corresponding index. So let's actually just analyze what this does by itself before we type anything else out. So I'm going to exit out of this. I'm going to clear what we have right now. Then I'm going to say we're going to run mass rates. So look what we have here. It says choose a substance to pick from. 1 is benzene, 2 is toluene, 3 cyclohexane. Select substance using the correct index. So if I wanted to pick toluene, I would select 2. Currently nothing else happens right now, but that's okay. We're going to get to that soon. Let's clear what we have. Let's go back to our script here, and let's go back to our algorithm actually. So the next step is to ask the user to enter 3 separate stream velocities as a vector. So once again, we can use input for someone to just enter a vector in for us. So what we can do is for our next part, we could say ask user to enter 3 input streams. So let's see, then what we're going to do is we're going to fprintf. Actually, no, we're not going to do that. We're just going to have them input the 3 right away. So we can say streams equals input, enter the 3 input streams in meters per second as a vector. So that will just directly ask them for the 3 input streams, and the user can enter them as a vector. Let's see what's next in our algorithm. Ask the user for 3 cross-sectional diameters of the corresponding pipes in centimeters. So use the input function once again to retrieve these values. So once again, the user is going to enter 3 values as a vector. So I'm going to say 3 input streams and diameters, just so we can put these both in one block. And then I'll put diameters equals input, enter the 3 cross-sectional diameters in centimeters, just like that. So then I ask the user for 3 different vectors for our input streams and 1 vector with our 3 input streams, 1 vector for our 3 cross-sectional diameters in centimeters. So let's see what's next here then. So we have essentially all of our data though. We have all the data now. We have what substance they want. We have the densities of those substances. We have all the linear velocities, and we have the cross-sectional diameters. With all this information, we can solve exactly what we want, which is the mass flow rates. So for each of the 3 streams, use the equation, and this is the equation here, mass flow rate equals density times linear flow rate times cross-sectional area. So if you think about it, first we need to calculate a volume. The volume is by using the linear flow rate passing through the cross-sectional area, because the linear velocities in meters per second, we can convert that to centimeters per second. Centimeters per second, we can find the area of the pipe by using pi r squared for the circle. Because if you think about it, we have a circle with a diameter of whatever the user entered. We can calculate the volume by doing pi r squared for that diameter. Instead of using the d for diameter, we have to divide by 2 to get the radius. Calculate the area of the circle, pi r squared. Multiply that by the linear flow rate. That will give us centimeters cubed. At that point, we have a volume. Since we have the volume in centimeters cubed, we can multiply by the density of whichever one the user inputted, either benzene, toluene, or cyclohexane. If we multiply the centimeters cubed by our density, we get a number of grams. Like if we had cyclohexane, 0.779 grams per centimeter cubed, by some volume in centimeter cubed will equal the mass in grams. Then, since this information must be depicted in kilograms per second, we must convert from grams to kilograms. And I'm going to show exactly how to do this in MATLAB. If the equation doesn't make all too much sense and you're not a chemical engineer, it's completely okay. It's understandable. This is just mostly to show how we can write these scripts in MATLAB and the kind of thinking that's required when going about all this and how a lot of the thinking is mathematical. So then let's take a look at what we need next. We need to actually calculate the three separate values we have, the three separate mass streams or mass flow rates. So what we can do here is, so we have our streams. These are our linear streams. So let's see, what can I call these? I'm going to call, let's see, we can make a new variable. First, I'm going to say calculate mass flow rates. So since the user entered 3 different streams with 3 different diameters, we have 3 separate mass flow rates to calculate. So in order to do that, I'm going to first start by making a new variable called mass streams. And I'm going to start by making that just an empty vector right now, because we're going to add numbers to this vector. So we want to calculate the 3 separate mass streams all together. So mass streams 1, the first one, is going to be the first value. This is where a lot of parts start coming together, so let's see, you can rewind if parts of this don't exactly make sense, but we're going to use a lot of different components of what we have here. So let's see, the mass stream, so the mass flow rate is going to equal, first we have our density. The density is going to be specific, depending on which substance we chose. However, the user entered a number. That number told us which density we want. If the user entered 1, we want benzene. If the user entered 2, we want toluene, etc. So that means that if we want the density for benzene, we just have to take the number we were given, which could be 1 for example, and we can index densities to get exactly the density we want. So in parentheses, I'm going to say, oh, not down there. I'm going to say densities, and then I can't just put densities because that's the whole vector. I need to give a specific number. Remember, densities of 1 would give us the first density, but we don't know which one they entered, except through this number here, n. N contains the number we want. If the user entered 3, we want the third value. If the user entered 2, we want the second value. If the user entered n, we want the nth value. So in parentheses, we're going to enter the number n, since that stands for the index of our matrix we want. Another thing to consider here is that our density is in grams per cubic centimeter. However, we want our final answer to be in kilograms. To convert from grams to kilograms, we have to divide by 1,000, meaning we're going to divide our density by 1,000. So that's the first part we have here. So we have our density. We need to multiply that by the linear flow rate. The linear flow rate is in meters per second. However, we're using densities in per cubic centimeter. So we need to convert our flow rate in meters per second to centimeters per second. So we're going to start by doing this. So once again, we're calculating the first mass stream, meaning we're going to be looking at the first linear stream we have, meaning we're going to multiply this by streams of 1, and then since we're converting from meters per second to centimeters per second, we need to multiply by 100. Then the final part we have here is we need to multiply by the, oops, I skipped ahead for a second. We need to multiply by the cross-sectional area, which is calculated by using pi r squared. We have the diameter, so what we need to do is multiply the diameter by 2, square it, and multiply by pi. So this will be accomplished by, make sure all my parentheses are good. Yep, they are. Multiply by pi times, we need the diameter we wanted. Once again, we're looking at the first stream, so we're going to use the first diameter that was entered. So diameter is 1 divided by 2 squared. And we have exactly that. That is the line of code we're going to use to calculate the mass stream. The density, whatever substance we're looking at, the nth substance, that's the number we use for our index. Divide by 1,000 to convert from grams to kilograms. Streams of 1. Streams 1 represents the very first stream they entered. Multiply by 100 to convert from meters per second to centimeters per second. Multiply by pi times the diameters of 1 being the first diameter entered, divided by 2, because we want the radius, square that radius, and multiply by pi. It's a bit, and this is kind of an advanced problem for starting off, but once again, this algorithm isn't something that you can just think of right away. Listing those steps isn't something you can immediately do. Something like this takes time and takes practice and takes a lot of work needed to get put in to be able to develop a solution you can use right off the bat. This is how you calculate one of the mass streams. We can calculate the other ones by using essentially the same technique. In fact, I'm going to simply copy and paste this, except change a couple of values. Instead of streams 1, I want streams 2. Instead of diameters 1, I want diameters 2, because we're looking at the second stream now. To calculate mass streams 3, I can say densities n. Oh, why am I actually doing that? I can just paste it once again. Instead of 1, I have 3. Instead of 1, I have 3, because we're calculating the third. N stays the same, because once again, we're dealing with the same substance all 3 times. That's how you get the 3 values. The last thing we're going to want to do is print all this in a way that makes it look nice and organized. So how we can do this is print values to user. We can do this by using fprintf. So once again, what we can do is we can use fprintf. I know I've been talking for a while, so I'm going to try to hurry this up. We can use fprintf to print everything in a very nice manner. So we can fprintf. We're going to do a couple -n's so that we can give a little bit of distance between everything the user already entered. Then we can say stream, so that they know what stream we're dealing with. And then, let's see, put a colon. I think I'll put that for now. And then stream, and then we're going to put mass flow rate, put a -n. So we have exactly that. And so then what I'm going to do, kind of like I did in a previous example, I'm going to put a series of equal signs so that we're just making a little table for ourselves. And then we're going to start by entering the values. So the first value we're going to enter is stream 1. So I can say stream 1, and then I put my value. I put my value to 2 decimal points because it's a float again. Put -n for a space, and the value I want to print here is mass streams of 1. Then I can do the same thing. I can say fprintf stream 2. I want to go to 2 decimal points, mass streams 2, and then I can do the exact same thing. I'm just going to copy and paste at this point, mass streams 3, and that will print the 3 values that I want. So let's actually try this whole script and this whole thing we created to see if it all works together. So I can try running it, and let's see. At some point you might realize you have a bug, and a bug meaning you have a problem in your program, and you want to try to fix it along the way. So let's see. Select the substance using the corresponding index. So we have 1, 2, and 3. Let's deal with cyclohexane. So I'm going to enter 3. Enter the 3 input streams in meters per second as a vector. So for our 3 input streams, let's try 12.3 meters per second, 5.6 meters per second, and 36.2 meters per second. Enter the 3 cross-sectional diameters in centimeters. So in centimeters, let's do, for diameter, let's do 10.2 centimeters. Let's do 6.7 centimeters, and let's do 4 centimeters. So you can see here, we click, I have 2 spaces because I did -n twice right here, and then it prints everything out pretty nicely. It gives a stream, the mass flow rate, and it says exactly what we want. The stream 1, stream 2, stream 3, and it prints the mass flow rate exactly the way we want to. It does exactly everything. So this is it's more of an advanced example. If you see, we have quite a few lines of code here and everything. We have comments to show exactly what we did. Once again, the algorithm for developing this isn't straight off the bat. It's something that you have to sit down and analyze and develop yourself, and it only really happens by practice and doing it multiple times and trying it multiple times. So I know I've talked on for quite a bit, but I'm going to look at one more concept here, and it's a function in MATLAB. So a function in MATLAB is very similar to a script, except functions revolve around specific variables for input and output instead of asking the user. For functions, users must instead enter an input value in parentheses after the function name. And we're going to show an example of this, but essentially, instead of a script, What a function will do is take in a value and give out a value instead of specifically asking the user. And so we're just going to do an example. Most functions can return one or more values. The beauty of functions is that they're able to interact with each other in MATLAB, and more on functions will be discussed in a later video. But I'm going to do one example. I'm going to turn the sphere to volume script into a function. I'm going to show you exactly how I do that. So instead of starting by just a document, a code, or typing code, I'm going to say function, then I'm going to say what my output variable is, which is volume equals sphere volume, which is the name of my function, and then an input variable, which is radius. So what this is saying is this code is a function. It gets put in a radius, and the output is a volume. Okay? Then what I can say here is I can say simply volume equals 4 divided by 3 times pi, this is just the equation for volume of a sphere, times the radius to the third power. And then every time you finish a function, you type the keyword end to know that the function is over. So there wasn't all too much to this function, and a lot more functions are complex, but if you look here, we are already assuming that we have a starting value, and that starting value is radius. We use that starting value here in this code to produce this output variable, which is volume. And MATLAB will know exactly what to display because it'll look for the matching word, volume to volume. So let's actually try this one out and see what will happen because of it. So I'm going to clear everything here. So I can say sphere volume, but look what happens if I just don't enter anything. There's an error. It says not enough input arguments, because as we specified in our function, we need an input variable, the radius. So instead what I can say is sphere volume, and then in parentheses I need to put a radius. So for my radius, let's do the previous example. I'll say 6 is my radius. If I click enter, it gives me the same output, but instead of saying volume equals, it says answer equals, like a lot of the function we've been dealing with earlier. This is exactly the format we want and exactly what we expect to see in MATLAB. Once again, this video went on very long. I apologize, and we will do a lot more on functions later, but I really hope those examples provided a good fundamental for how code should be practiced in MATLAB and how you should be writing scripts and functions in your own time. Thank you so much.